So welcome back to our third lecture in the probability review series. This lecture covers univariate random variables and distributions. We will look at two types of random variables, discrete and continuous. So what is a random variable? Well, a random variable is really misnamed. It's not a variable, it's a function. And it's a function from the sample space onto the real line or a subset of the real line. So for example, we can think of our sample space of admission to UVA as admit, don't admit, or wait list. We could put that on the random line. One way we could do that is to put it on three numbers, 0, 1, and 2, for example. Or we could take the flip of a coin and put it on the two numbers 0 and 1. We could take the time until a car has a flat tire and consider that to be a subset between, let's say, the present time and sometime several years in the future. So notice that in one case where we have countable outcomes and in another case we have uncountable outcomes. And that's what we mean when we break random variables into two parts. Discrete random variables, these have at most countable numbers. It doesn't mean that they may not have an infinite number, but we can count the number that they have. Or continuous random variables, which are uncountable sets of values. So time would be an example, time between intervals, let's say the current time, and as I said, sometime in the future of about a couple of years or even a month. That kind of counting, that kind of uncountable set is what we consider to be a continuous random variable. So we define probability mass functions on discrete random variables. And these look at the points, for example, the 0, 1 points in a flip of a coin, and they put a probability on those points. That probability then is that combination of probabilities across all the points or some subset of points is considered to be a mass function. And over all points that it could take on, it would be the probability mass function for that random variable. The cumulative distribution function just sums the values of the probability mass function up until a particular point. So if, for example, if we're thinking about admission to the University of Virginia, we've coded that as 0 is not admitted, 1 is waitlisted, and 2 is admitted. Then we could look and say maybe the probability of each one of those outcomes is 1/3. Then we'd say the cumulative distribution function for points 0 or less, which is to say being rejected, is 1/3. The probability of being at least waitlisted, which is 0 and 1, would be 1/3 plus 1/3 or 2/3. And the whole distribution function, cumulative distribution function, then looking at all possible outcomes would be 1. The Bernoulli distribution is the simple probability mass function. The random variable in this case takes on two values, 0 and 1, 1 with probability p and 0 with probability 1 minus p. The mass function then looks as shown with n choose x, where x is the number of ones or successes that we observe in n trials of n Bernoulli trials. And that would then be p to the x1 minus p to the n minus x. The distribution looks like this when we look at different values for p for over n possible trials. When p is 0.5, we see that it's nicely symmetric. About 5 is the number of ones we would expect to see in n trials. But there's a pretty good chance we would see 4 or 6. Not a bad chance that we would see 7 or 8 and so forth. We see, though, that as p gets smaller, going to 0.2, the chance of getting these larger numbers of ones in 10 trials begins to shrink. And it gets smaller and smaller. And by the time we get to a probability of a 1 at 0.01, we see that there's actually a little likelihood of us getting 2 successes and certainly a relatively small likelihood of getting even 1 success in 10 trials. The Poisson distribution is a very useful distribution since it also models counts. So again, it's looking at the number of occurrences. X can take on values 0, 1, and so forth, all the countable values. It has one parameter, and that parameter is called lambda, and lambda must be strictly positive. The probability distribution is as shown, or the probability mass function, is as shown, e to the minus lambda, lambda to the x factorial. When we look at a plot of the Poisson distribution, we see that when lambda is 0.5, it's heavily skewed to the left. And as we increase lambda's size, we get different possible probability mass functions across the counting variables. The Poisson distribution was originally used as a way to count the number of Prussian army soldiers who were killed each year by being kicked to death by their horses. So it's a relatively rare event, but it's found a lot of use in a lot of practical applications, including in communications and in cybersecurity and things like that. Okay, let's now look at continuous random variables. Continuous random variables take on values across an uncountable set of the real line. So for some subset of the real line, say A, then we can define some function f of x, such that if we integrate over A, that function, then that gives us back the probability that our random variable occurs within that interval of the real line. So this would be a way, for instance, for us to find the probability that flat tire occurred, let's say, between 1 month and 6 months out. The cumulative distribution is defined as an integral now instead of a summation, as we saw in the discrete case. And this integration starts at minus infinity and goes to some point A. So we integrate our probability density function from over that interval, and that's how we define our cumulative distribution function. Look at an example of that. So let's consider a probability density function. F of x is equal to x, so it's the identity function between 0 and the square root of 2. And then this density function is 0 otherwise. So how would we graph f of x and the density function and the cumulative density function? Well, it turns out that we can do this quite easily, of course, since it's just the identity function between 0 and the square root of 2. And then after that, it's 0 everywhere else. So it's just this linear function. But we see that when we look at the cumulative probability function, when we take the integral over that linear function, we get this nonlinear function that rises quickly to 1 as x approaches the square root of 2. Some common continuous distribution functions that we'll use. The first one is the uniform. The uniform is a flat distribution between some points A and B or some interval of the real line. We can look at examples here. Between 0 and 1, it rises to the value of 1 and is 0 everywhere else. Uniform distribution between, let's say, 0.5 and 3 is given by the orange plot. And we see that somewhere less than 0.4, say about 0.35. In that interval, and we can define it over any intervals we want, even negative. So between minus 0.5 and 3.5, we see an example of what the uniform looks like there. Again, it's flat over the interval of the real line that we've chosen. The beta distribution is a very useful distribution for us in Bayesian probability modeling, and it's given by it's a probability density function that's defined for a random variable that takes on values between 0 and 1. So in that interval between 0 and 1, it has two parameters, A and B, and those A and B are used as a way to define this probability density function. And you can see the description of the probability density function there. In the denominator, it has a beta function, B of AB, and that's given by the integral of what we consider to be the kernel of the density function. So that's actually a normalizing constant. So that's a good example of how we create a probability density function that normalizes to 1 over the space that we're interested in. Here are examples of the beta distribution between 0 and 1. And we can see it has a variety of different shapes. When A is 1 and B is 1, we get back actually a uniform density function. when A is 0.5 and B is 0.5, we get back a what's called a bathtub distribution. This distribution is useful in reliability and maintainability analysis, since things like electronic components frequently behave this way. They have a burn-in time in which a lot of them might fail because of defects in the manufacturing process. But if they're good, they will last a long time until they reach the end of their life period, and then they tend to fail rather quickly. And we can see that we can get unimodal distributions. We can get different shapes of them based on things like A equals 3, B equals 3, A equals 3, and B equals 1. Different shape distributions. The gamma distribution is very useful for random variables that are non-negative. So in this case, x can only be greater than or equal to 0. It has two parameters, lambda and alpha. The probability density function is as shown. Notice that it has something that we call a gamma function, and it's also known as the Euler's gamma function after the mathematician Euler. And it's given by the integral equation that's shown on the slide. When alpha is a positive integer, however, this gamma function has a convenient form and in fact takes on a factorial form. It's also possible to write that beta function that we saw earlier as a composition of gamma functions. The gamma function also can take on a variety of different shapes, and these are different examples of shapes that are taken on based upon the different shape parameter in the density function. The Gaussian distribution is a common and widely used, and we'll find lots of opportunity to use it in our Bayesian machine learning course. It's also known as the normal distribution function. We'd prefer to call it Gaussian because normal takes on this meaning in the English language, and random variables that are normally distributed may not be normal. So we'd prefer to call them Gaussian distributed. And there's the density function for the Gaussian. It's a well-known function. The Gaussian function has a lot of nice properties. One of them is given here, that if we scale it and translate it, scale it by A and translate it by some amount B, then it turns out that we get another Gaussian that's been scaled and translated in its first mu parameter, and it's been scaled in its second parameter, the sigma squared parameter, accordingly. The Gaussian distribution is well known. It has this bell-shaped curve, but you can see that that second parameter, that sigma squared parameter, determines how flat it gets. And in this case, when the sigma squared gets to 5, you can see it tends to flatten out quite a bit. The t distribution is an extension, if you will, of the Gaussian, and its probability density function also uses those gamma functions to normalize, to make sure that it integrates to 1. It has three parameters, mu, sigma hat, and nu, where mu is the location parameter, nu is the degrees of freedom, and sigma hat is the scaling parameter. This t distribution has a nice property that it converges to the Gaussian, so that as the degrees of freedom get large, and it turns out they don't have to get very large, about 30, and they're pretty close to the Gaussian. And when nu is 1, this distribution has it's what we call a robust distribution, in that it tends to have very large tails, and so we use this frequently when we're really uncertain about what outcomes might occur over a portion of the real line. These are pictures of the t distribution with different values of the degrees of freedom parameter. You can see that at 30 it looks very much like a Gaussian. At 3 you can see that it has much wider tails than the Gaussian distribution does. And when it gets to degrees of freedom 1, that Cauchy distribution, it really has much wider tails. It's peaked over its location parameter, but it has very, very wide tails. And those are examples of univariate distributions that we'll be using in machine learning. And in the next class, we'll talk about moments of random variables.